Okay, let us start the problem. Uh, a steel plate width of 120 mm and of thickness 20 mm is bent into a circular arc of radius 10 meters. Radius 10 meters. Okay, then determine the maximum stress induced and the bending moment which will produce the maximum stress. Okay, so take Young's modulus E is equal to 2 into 10 to the power of 5 newtons per mm square. 2 into 10 to the power of 5 newtons per mm square. Okay, so a steel plate width of 120 mm and of thickness 20 mm. Okay, so one steel plate is given with a width of 120 mm. Okay, and its thickness is given as 20 mm. Thickness is given as 20 mm and which was bent into a circular arc of radius 10 meters. Okay, so R is given as 10 meters. Determine the maximum stresses induced and the bending moment which will produce the maximum stress. Okay, and here E value is taken as 2 into 10 to the power of 5 newtons per mm square. Now coming to the solution. So width of the plate is equal to B, that is 120 mm, and the thickness is T, that is 20 mm. Then the moment of inertia I equal to B into T cube by 12. Moment of inertia is BD cube by 12. Here instead of D we know that is thickness. Instead of depth they have given thickness, that is T. Okay, so written as BT cube by 12. So B value is given, that is 120 into T value is T value 20 cube by 12. 20 cube by 12. So when we have calculated it, you can find So 8 into 10 to the power of 4. Eight into 10 to the power of 4 mm to the power of 4. Mm to the power of 4. So it is in mm and this is in mm cube. Mm cube, mm to the power of 4. Okay. So next one is radius of the curvature is given. That is radius of curvature. It is given as 10 meters. So we can convert into millimeters. We can convert into millimeters. So 10 into 10 to the power of 3 mm. 10 into 10 to the power of 3 mm. Okay. Okay. Now let maximum bending moment is equal to maximum stress induced. Maximum stress induced and m is the bending moment. M is the bending moment. Okay, so using the formula, previous formula, this is sigma b by y is equal to sigma b by y is equal to E by R. Sigma b by y is equal to E by R, where sigma is the stress. Okay, using that formula, sigma by y is equal to E by R, where here sigma is equal to E by R into y. Okay, so this is the stress at a distance y from neutral axis. Okay, so this formula is applicable only for pure bending. So we have to find the maximum stress. Okay, so stress will be maximum when y is maximum. I have already told you that is stress is proportional to y. Okay, so if stress is maximum and y is maximum, but here y will be maximum at the top layer or bottom layer. It will be maximum at top layer or bottom layer. So y maximum is equal to T by 2, which is 20 by 2, it is 10 mm. Now so write it as equation number 1. So equation 1 can be written as, sorry, my writing was not good. Okay, you have to follow my words. Okay, right. So maximum maximum stress is equal to E by R into Y maximum. E by R into Y maximum. So E by R, E is given as 2 into 10 to the power of 5 by R is 10 into 10 cube into Y is 10. Y is equal to 10. So which will give you 200 newtons per mm square. Okay, so the first question, maximum stress is equal to 200 newtons per mm square. Okay, next, another equation, that is m by I equal to E by R. M by I is equal to E by R. Okay, so from this, m equal to E by R into I. So we know E is 2 into 10 to the power of 5. R is 10 into 10 to the power of 3 into I value, I value 8 into 10 to the power of 4. 8 into 10 to the power of 4. Okay, so when we have calculated it, you can find 16 into 10 to the power of 5 Newton millimeter, or you can also say it is 1.6 kilonewton meter. So this is answer. So this is the maximum bending moment occurred. Okay, maximum bending moment is 1.6 kilonewton meter, and the maximum stress is 200 newtons per mm square. Okay, right? Okay, now we can solve another problem. Okay, calculate the maximum stress. Maximum stress induced in a cast iron pipe of external diameter 40 mm of internal diameter 20 mm, and so 40 mm external diameter 40 mm and internal diameter 20 mm. Okay, means thickness is 20. Okay, and 20 mm, and of length 4 meters. When the pipe is supported at its ends carries a point load of 80 newtons at its center. Okay, calculate the maximum stress induced in a cast iron pipe of external diameter 40 mm and its internal diameter is 20 mm. Okay, and the length of the pipe is 4 meters, and the pipe is supported at its ends and carries a point load of 18 newtons at its center. Okay, means suppose we consider the cross section of the pipe. Its diameter is 40 mm from outer to outer, and internal this 20 mm. Okay, so this is internal diameter, and it's not a circle. Okay, external diameter. So external diameter with 40 mm, and the internal diameter is with 20 mm. Okay, so this pipe is supported at its ends. So simply supported. This pipe is supported at its ends and carries a point load of 80 newtons at the center. It is carrying a point load at its center with 80 newtons. Okay, its length is 4 meters. Its length is 4 meters. Okay, so this is the problem given. Okay, solution. So given data is external dia, that was D 40 mm. Okay, next internal dia, that is small d, is 20 mm. Next, length of pipe, that is 4 meters, or which is equal to 4 into 10 cube, or 4000 mm. Okay, next, point load W, which is equal to 80 newtons. So it is a simply supported beam, so carrying a point load. Okay. Point load at the center. Okay, so the maximum bending moment is available at center. So the maximum bending moment is at the center of the beam. Okay, maximum bending moment is available at the center, right? So maximum bending moment is equal to W into L by 4, so which is equal to 80. W value, point load is given as 80, length is 4000 mm by 4, 4000 mm by 4, so it is 8 into 10 to the power of 4 Newton millimeter, 8 into 10 to the power of 4 Newton millimeter. So maximum bending moment M equal to 8 into 10 to the power of 4 Newton millimeters. Okay. Right. Here this is the cross section of a pipe. This is the cross section of a pipe. Okay, for the pipe, the moment of inertia is, okay, moment of inertia of, and it is a hollow pipe, okay, of a hollow pipe, I equal to pi by 64 into d to the power of 4 minus small d to the power of 4. Capital D is external diameter and small d is internal diameter. Okay, capital D is external and small d is internal, so which is equal to pi upon 64 into d to the power of 4, so 40 mm to the power of 4 minus 20 mm to the power of 4. Okay, so you have to calculate it. Pi by 64 into 40 to the power of 4, 25,000, sorry, 2 lakhs 50, 1 2 3 4 5 6 7, okay, 25 lakhs 60,000, 25 lakhs 60,000 minus 20 to the power of 4, 1 lakh 2 3 5 6, 1 lakh 60,000, 1 lakh 60,000, so that is 25,000, sorry, 25 lakhs 60,000 minus into pi divided by 64. Okay, 1,17,809.7 millimeter to the power of 4. Okay, 1,17,809.7 millimeter to the power of 4 is moment of inertia. Now, using the formula, m by I is equal to sigma by y. M by I is equal to sigma by y. When y is maximum, stress will be maximum. Okay, so y maximum, which was available at the top layers, y is maximum at the top layers. So therefore y maximum is d by 2, that is 40 by 2, 20 mm, that is 20 mm. So therefore the previous formula, so this formula can be changed as m by I is equal to maximum sigma maximum by stress maximum by maximum stress by y maximum, or maximum stress is equal to m by I into y maximum. So m we have calculated as 8 into 10 to the power of 4. 8 into 10 to the power of 4 by I value 1,17,809.7 into y maximum is 20. Okay, so which was equal to 8 into 10 to the power of 4 to 10 to the power of 4 into 20 divided by 1,17,809.7. So that is 13.58 newtons per mm square. So this is in mm to the power of 4, and this is mm, and this is mm. So mm 2 times, so mm square, newtons per mm square. So maximum stress is 13.58 newton per mm square when the bending moment is equal to, maximum bending moment is equal to 8 into 10 to the power of newton millimeter. Okay, 8 into 10 to the power of 4 newton millimeter. So this is the answer. Right, now we will see next topic, that is section modulus. Section modulus. Okay, so it is defined as the ratio of moment of inertia of a section about the neutral axis to the distance of the outermost layer of the neutral axis. Okay, right? That is, it is defined as the ratio of moment of inertia of a section about the neutral axis to the distance of outermost layer from the neutral axis, that is y maximum. Okay, so mathematically the section modulus is denoted as z. Section modulus is denoted as z, which is equal to I, moment of inertia, upon y maximum. Okay, z equal to I by y maximum. So for section modulus, units of z is, so moment of inertia is millimeter to the power of 4 and y is millimeter. So millimeter and power 4. So if it is get cancelled, we have millimeter to the power of 3, or we may also written as centimeter to the power of 3 centimeter cube or meter cube. So these are the units of section modulus. Okay, here the stress, sigma will be maximum. We know this y is maximum. Okay, sigma will be maximum, means stress is maximum when y is maximum. Hence m by I equal to sigma maximum by y maximum. Therefore moment of resistance m equal to sigma maximum into I by y maximum. And we know I by y maximum is equal to the sectional modulus z. So therefore moment of resistance m equal to sigma maximum into z. Okay, so here m is the maximum bending moment. M is the maximum bending moment. So moment of resistance offers the section is maximum when the section modulus z is maximum. Okay, so moment of resistance offered the section is maximum when the section modulus z is maximum, right? Moment of resistance offered the section is maximum when section modulus, that is Z, is maximum. Now we will see section modulus for, we will find the section modulus for various shapes or beam sections. Okay, so in which first one is a rectangular section. See, a rectangular section. Okay, so this is a rectangle having x-axis and y-axis. Okay, so this is a rectangular section, a solid rectangular section having a width of b and a depth of d, having a width of b and a depth of d. Okay, so y maximum is occurs at d by 2. We know y maximum is occur at d by 2. Okay, for a rectangular section, moment of inertia about x-axis is equal to b d cube by 12 and y maximum is d by 2. Y maximum is d by 2. So the section modulus z equal to I by y max. The section modulus z equal to I by y max. So section modulus about x-axis is equal to Ixx by y maximum, that is Ixx is b d cube by 12 whole by y maximum is d by 2. Equal to b d cube by 12 into 2 by d. Okay, so 6 2. So zxx equal to bd square by 6. Similarly about y-axis, zyy equal to db square by 6. Okay, db square by 6. So this is for rectangular section. Next we will see circular section. Okay, a circular section. This is a circular section, also having x and y axis. Okay, with a diameter of d. Okay, so this is y maximum equal to d by 2. Okay, it is a circular section, all sides the radius are equal, so Ixx is also equal to Iyy. Ixx is equal to Iyy, that is equal to pi by 64 d square, and y maximum is d by 2. So zxx, which is also equal to zyy, is ixx by y maximum, that is pi by 64 into d square whole divided by d by 2. You can write it as pi by 64 into d square divided by 2 by d. Okay, so 264 is cancelled. Sorry, d to the power of 4, d to the power of 4, pi by 64 d to the power of 4. So pi by 64 into d to the power of 4 divided by d by 2 by d. So 2 and 64 get cancelled, which is equal to 32, and d is cancelled. So zxx equal to zyy is equal to pi by 32 into dq. So this is the section modulus for circular section. Next we will see hollow rectangular section. And also a hollow circular section. Okay, so this is a hollow or rectangular section. So here consider the outermost width b and the innermost width small b. Outermost width is capital B and innermost width is small b. So it is also having two axes, x and y. Similarly, outermost depth capital D and the innermost depth small d, and y maximum is capital D by 2. Y maximum is capital D by 2. Okay, so here Ixx equal to PD cube minus, so it's a hollow section, so small b d cube by 12, and y maximum is d by 2. Therefore the section modulus zxx equal to Ixx by y maximum, that is bd cube minus small b d cube by 12 divided by d by 2. So you can write it as b d cube minus small b d cube by 12 into 2 by d 6 times, which is equal to b d cube minus small b d cube by 6 d is zxx. Similarly, zyy is equal to d b cube minus small d b cube by 6b. Okay. Next, the hollow section. Hollow circular, for hollow circular section, so we have two diameters. One is the inner diameter and another one is the outer diameter, and it is a circular section. So both x-axis and I-axis and I-y-y are similar. So z-axis and z-y-y section modulus are also similar. So inner diameter is considered as small d, and the outermost diameter is considered as capital D. Okay, so yeah, Ixx, which is also equal to Iyy, is equal to pi by 64 into d to the power of 4, capital D to the power of 4 minus small d to the power of 4. Similarly, y maximum y, which is d by 2, equal to d by 2. So zxx, which is also equal to zyy, is equal to Ixx by y maximum, that is pi by 64 into d to the power of 4 minus small d to the power of 4 all divided by small d by 2, capital D by 2. It is, you can write it as pi by 64 to d to the power of 4 minus small d to the power of 4 multiplied by 2 by d. So zxx equal to zyy equal to pi by 32 into d to the power of 4 minus small d to the power of 4 divided by capital D. So this is the section modulus of a hollow circular section. So in this section we have seen what is section modulus, okay, its definition, and various examples or various cases of section modules.